Hear me?
Yeah, all good.
Okay. Well, I should start with a big apology. I messed up the time zones. Thank you for converting the time zones for us, but then I read them as U.S. time zones. I read them as West Coast time zones, not East Coast time zones, and I should have done my homework. It's entirely my fault, and I thank my colleague Maddie Smith for letting me know that I had missed the meeting. And I'm sorry I missed yesterday. Also, that would have solved this problem on the front end. So my apologies. But I'm here now, and I'd like to tell you about some data that's available and hope that it excites others to use it and hope that you can broadcast it through the community because it's become quite a long data record, and I think it might be useful to the community. So I like to start with just a video of what we study, right? There's some waves that are being generated offshore here in this video, and it's a short wave field. The winds are maybe 10 meters per second, and there's 1 meter waves at about 5 or 6 seconds, and there's a little bit of white capping, and then they come into this marginalized zone, and they're rapidly attenuated. And there are all sorts of interesting things in this video. There's some inhomogeneity in the ice, which is common but very problematic. And there's some real strange shapes at the ice edge. It's not a straight ice edge, and so you can see all the challenges that we face, and that's just for a single case. And when you start to look at a very large data set, you have so many underlying conditions. It's a bit there's a lot to look at, but hopefully I can show you that it can still be useful. I have some co-authors, and they are the folks at Woods Hole and at Yale who helped make these observations and keep these observations going. Okay, so a quick outline. We have 12 years now of mooring data from 2 locations in the Beaufort Sea in the Western Arctic. They're almost contiguous, as I'll show you. There are a few gaps. They are completely annual time series. So there are times when there are no waves and complete ice cover, and there are times when it's complete open water and there's lots of waves. I'll show you that the wave climate is increasing. I think we all know that, and there's been a lot published about that, but I'll just emphasize it again. And then remind us that wave attenuation in ice happens all the time. And we usually think about it when we go do a big experiment. We put out a lot of buoys, or we do a laboratory experiment, or we run some analytic and numerical models. We think about very specific cases, but actually it's happening all the time. And it really has a much wider range probably than we appreciate. And then I want to talk about process and talk about a few things that are a little bit beyond just the regular how are waves attenuated in sea ice, and what's the form of that, and what's the proper way to capture that, but to talk about what I consider the so what, what happens afterwards. And I think that it's the so what when we talk about climate system models and the larger ice ocean atmosphere interactions. It's that these waves, they carry momentum, and they carry energy. They carry fluxes of momentum and energy, and when they enter the MIZ in the marginalized zone, they release some of that momentum and energy as part of their attenuation, at least when they're dissipating, not scattering. So we can have a good talk about that. But anyway, then I want to also talk about wave generation in ice, because I think that's a fascinating topic about local generation rather than just wave energy propagating in. Okay, and if I have time, I'll talk about coastal wave exposure. There was this nice special issue last year celebrating Vernon Squire and his contributions, and I just want to point you to this paper where we talk about this long-term data set. And so if you want some more information about the data set, this paper is one place to look for it. I think the special issue is also great, and I appreciate the community came together to do this special issue. And there's a link if you want it. So overview, there's less ice across the whole Arctic. I think everyone's very well aware. Here's one particular example when the map shows the ice cover in September of 2020, and that's the white part. That's where the ice actually was in 2020. And then the yellow line is where the ice used to be in prior decades in the minimum that happens at the end of the northern summer. So there's a lot less ice. And by being a lot less ice, there's a lot more fetch. So we have shown in a series of papers that if there's more fetch, then there are more waves. It's very simple. You don't need a complex model. You can do a very simple analytic model and show this. And it really does not require any changes in the wind climatology. You just need more space, and with more space, we'll grow more waves. So I think surface waves in the Arctic in particular, are becoming a more important part of the whole coupled system. That's really the point I want to make. So this is non-dimensional wave energy versus non-dimensional fetch, and it's certainly a control on wave energy in the Western Arctic, in the Beaufort. And here are some model results where you can do this over the last 30 years. And you can take big averages and standard deviations over a whole spatial domain. And you can see that on average, wave heights are increasing and wave periods are increasing. And that's also related to fetch, right? Because if there's a longer fetch, then waves have more time to become fully developed, and they can become no longer fetch limited, but now they can be either duration limited or they can get to a fully developed sea state. So it would make sense that wave periods would also get longer. But there, at least in this model result, there's no trend in the wind speed. You don't need a different wind forcing to have these effects. You just need more fetch, which is directly related to less ice. Okay, so here's the data. This is the state of Alaska. The Beaufort Sea is up here, and this is the Bering Strait. So Russia, Siberia is over to the left there, and the rest of Canada is over to the right, to the east here. And then zooming in, here's the northern slope of Alaska. This is Point Barrow and the village of Utqiagvik. Here's the shelf, and then here's the deep basin of the Beaufort Sea. And the Beaufort Gyre Observing System has a series of moorings that are maintained by the Woods Hole Oceanographic Institution. They're labeled by letters. So there's BGELS A, B, C, and D. And it's moorings A and D that we've chosen to use for these long-term measurements. And you can see in this particular snapshot, this is in late September of 2021, I think. There's still quite a bit of ice cover at these moorings some of the time, but then there are also these pockets with less ice cover. And this, of course, is a very binary ice cover. You know, it's either present or absent, but we know that the sea ice concentration is much more complicated than that. This is just really to give you a sense of what it looks like in the late summer after some melt. Of course, in the winter, the entire region would be entirely ice covered, almost 100%. Here are the time series, and here's a bit more detail about the moorings. So the moorings look like this image at the bottom left here. They're subsurface moorings. They're tethered to the seafloor at 3,000 meters depth. And then the top part of the mooring is about 30 meters below the surface. And then it looks up with an up-looking sonar. The one we use is a Nortec AWAC. And you can see it here on this subsurface flow. This is the buoyant part. And then over here with the little blue transducers, that's the Nortec AWAC. So one beam looks up and then three beams fan out to the side. That beam samples at 1 hertz and gets statistics of the interface above it, the distance to the interface. And that can either be open water and then you measure waves, or it could be ice and then you measure the ice draft. So here are the time series starting in 2012. We have measurements of wave height. Now we actually have the full scalar wave spectra. So we do make a spectrum from these, and we even make the directional moments, although I will comment that they are pretty low quality because the heading is not very well established on this mooring because the magnetic readings are poor at this high latitude. And it's an older instrument that doesn't have corrections for that. But we do at least have the scalar spectrum. And you can see the wave heights are the integral from that spectrum, and they are generally, there's some signal in the summertime, in the northern summertime, and then there's nothing in the winter. And there's some years with nothing at all. And that is a combination of data gaps from instrument malfunctions and a combination from some years when these mooring locations are actually ice covered the entire year. They're far enough into the basin that the interannual variability of the ice really has a big control on the data set. Okay, the bottom panel is now, this is the ice draft, the ice thickness below the mean sea level. And you can see that data record is much more contiguous. And that's in part just because there's ice much more of the time. And the two different colors are the two different locations, mooring A and mooring D. So this is the data set that's available for people to work with. You can collapse this data set that spans these years into just the seasonal cycle. So I take all this data and I'll just show it to you now by month. And here's what that looks like. 2 axes, ice draft or ice thickness on the blue axis to the left, ranging over a few meters. 2 meters is pretty typical for the winter ice cover. And then over here on the right axis, these are the wave heights, and 1 to 2 meters is typical. 4 meter H-sig is the maximum that we've ever measured in the whole time. So right away, you should notice that that's much less than the Southern Ocean, much less, the wave energy is much less than it is along the Antarctic marginal ice zone. And that makes sense because there's less fetch, right? I mean, this is not the Southern Ocean at all. But they're still appreciable waves. They're still quite measurable. And they're very active in the late summer. That's the whole point. The seasonal signal is something that, you would expect. And you could have drawn the general shape of this without having any data. But now we have the data. Okay. So you can ask, how are these two things related? How much ice is there in a given year versus how many waves there are in a given year? Here's a very broad brush look at that, where I just look at the average annual significant wave height on this axis versus the average annual ice thickness, and just see on a year-to-year basis for these two things related. And they certainly are. There are more waves when there's less ice. Makes sense, right? It's almost a circular argument because, at a given mooring, you're only going to see any waves if the ice goes away. So, point wise, this certainly plays out to be true. But it is true over the larger domain as well. This is just one way to see it with in situ data at a given point. Okay, so what can we do with this data? I have been thinking about the whole system and this larger scale thing, instead of just doing these case studies that we typically do when you put out a whole bunch of buoys for one event for a few days. Now we have 12 years of data, so now we know the real range of conditions. So I did some thought experiments here where I do classic spectral attenuation, energy here decaying from a location at the ice edge, using an alpha here, and alpha is the classic power law as a function of frequency. I go to Mela 2018 and I pick a B of about 3, so that's the exponent, and I pick an A of about 10 to the minus 2, I think, and I get attenuation rates that are sort of 10 to the minus 5, 4-ish. And I look at the measured wave heights that we have out in open water from this data set, range from about 1 to 4 meters. And I just simply ask, how far do they make it into the ice? Right? If I just use literature values for attenuation, how far should we expect waves to propagate into the ice? Remember that I don't have great ice products and I don't have a whole array of buoys. I don't really know how far things are going. I'm just asking about how far does noticeable wave action make it into the ice. So that's the plot there. HS as a function of distance in kilometers. Sorry, we're missing an axis label there, but it will pop up eventually. And so you see that most of the energy, most of the wave heights, do this either way, but it's all pretty much decayed by about 100 kilometers. And I want you to, I'm going to circle back to that 100-kilometer number because I want to make this contrast with the Southern Ocean, where we do sometimes see waves propagate 100 or 200 kilometers into the Antarctic marginal ice zone. But that doesn't seem to happen in the Arctic, and I think that's just because the waves are smaller and they're shorter period, and that spectral aspect of attenuation is very important here. So lots of things happening, less than 100 kilometers, not much beyond 100 kilometers. Okay, what about momentum? Well, here I quantify the momentum flux using the classic radiation stress from Long and Higgins. And I ask, well, what is the gradient, spatial gradient in the radiation stress? And that would be, if the waves are truly dissipating, not scattering, as they go into the ice, then this calculation for the radiation stress gradient, d by dx of s to the, let's just say the sxx component for now of this radiation stress tensor, then that is the momentum that's being released as the wave field decays into the ice. And I think, personally, I think this is something that hasn't been studied very much and is worth further study, because it's really the momentum that gets released to the rest of the system. This is the momentum that can move ice and water around and be part of the rest of the system. So you can make this calculation pretty easily because the radiation stress scales with the energy in deep water, and it's a pretty trivial calculation. And then you can see here this release of momentum as a function of distance into the ice. And it goes down pretty rapidly. Maybe all the interesting stuff is happening within the first 50 kilometers. And then I make this comparison, which I think is instructive, and that's what these rainbow colored lines are here. These different color lines are, this is the equivalent amount of momentum being given to the ocean by the wind, just a wind stress calculation. The wind is blowing, we know the drag coefficient more or less, and we say how hard is the wind pushing on the ocean. And it gives us this relative magnitude to say, well, do we care? Does this matter at all? And I think the answer is within the first few kilometers of the marginal ice zone, we do care that the energy, that the momentum released by waves as they dissipate into the ice may be appreciable as a contribution to the momentum of the ice itself or of the ocean just below the ice. And it's something that we need to start thinking about in two-way coupled models and fully air ice ocean models, because it's on a similar order of magnitude to the wind. Okay, that's momentum. Now I also want to think about energy. So here then I look at the gradient of the energy flux, right? So waves carry an energy flux, ECG. I actually make this calculation spectrally. That ECG is done as a spectra with, CG is defined across the spectrum. And then look at the gradient of that. And that is the rate at which energy is lost, or it's really a dissipation rate, right? That is another way to look at attenuation. This is the rate that energy flux is lost. I call that W dot because it's the rate of work that the waves could be doing work on the ocean below, or could be doing work on the ice also, right? Could be flexing the ice, could be causing ice collisions, or could be causing turbulence in the ice. But if scattering is weak and dissipation is strong, the energy loss from the wave field has to go somewhere, right? And this is a calculation for what's going, or at least how much is being transferred. Similar effect here. I make a calculation for what the equivalent wind would be, and this is wind in meters per second. And you can see that that the rate that energy is being lost by the wave field, that's pretty, appreciable, or it's similar relative to the rate that the wind does work on the surface of the ocean. So we think about, how is the ocean mix layer going to evolve? This is possibly an important term. So really, I've just used this long-term data set to kind of do order of magnitude calculations, really toy models of whether this should matter. And my answer is that the momentum and energy from the waves probably matters in the first 25 kilometers of the marginal ice zone under these conditions, and probably mostly when there's an event and there are strong waves. Okay, I want to give some examples of that because some of these momentum and energy calculations might seem a little bit out of left field, or if people aren't familiar with them. So I want to provide some corroboration for them. So here's an experiment that we did in 2018 with a whole bunch of co-authors, including Maddie Smith. And there's ice here in the gray shading, and there's open water in the blue. We know that because we have these pictures. We were there, and we have these buoys that were in the open water and in the ice. We also have a radar, and that's what these scans are. The darkest grays are the radar scans from the ships. And the ship showed us where the ice was by using its radar to map that. We have very obliquely incident waves, and they drive motion along the ice edge. And the right-hand side here shows you that the wave height's attenuating with distance into the ice. 0 is the ice edge, and X is increasing further into the ice. That shape of the wave heights attenuating is very similar to the shape of the motion in the marginal ice zone. There's very strong motion, there's very strong transport right at the ice edge where the wave gradients are strong, and there's less and less as you go in. And we argue in this paper that that's because of these radiation stress gradients. So the momentum released from the waves is really driving transport of ice and transport of the water below, and that it's distinct from the wind. And you can make a calculation here, as I did in the last several slides, about what the wind would do. And there's the dashed line for what the wind would do versus what the waves would do. And you can see that you sort of asymptote to what the wind would do. And the conclusion is that the waves are doing something very localized at the ice edge, because that's where attenuation happens. And the wind is doing something on a much larger scale. And the momentum from both matters, but the wave momentum is probably being ignored. Okay, there's an example on momentum. Here's an example on energy. I'm going to turn to the same data set, this case study we did, where, again, wave heights are attenuated further into the ice, starting from X is 0, ice is 0. And this is a measurement of the in-water turbulent dissipation. This is made with Doppler turbulence profiles made from the buoys that we put out. And you can see very high levels of turbulent dissipation. So this is how much the ocean is stirring around, losing energy to heat and sound through its turbulence. And you can see these yellow colors. This is where there's very strong turbulence. And the argument here is that where there's strong gradients in the wave field and energy is being lost, that a lot of that energy is being lost to turbulence, because the waves cause the ice to move. The ice doesn't quite keep up with the wave orbital motion. There's a little bit of inertia and added mass, and such that there's a little bit of differential motion between each ice flow and the water below. And that's enough to have some shear at the interface and drive turbulence between the bottom of the ice and the ocean just below. And all that turbulence is an energy loss. We looked at that during some other experiments and came up with this overall correlation between the turbulent dissipation that we measure in the ocean just below the ice and the observed attenuation, the classic alpha of how wave energy is being lost. And we see that they're related. There's a lot of scatter. It's a complicated process, but they're related. So my argument here is that a lot of wave attenuation that we see in the marginalized zone is a dissipative process, and that energy is going somewhere. It's in large part going into turbulence in the ocean. It certainly can be going into inelastic collisions of the flow. It can be going to bending larger ice flows, lots of other physics there. But for small ice flows, I think they're mostly stirring up the ocean and causing turbulence. Okay. Last part of the talk, I want to talk about wind wave generation deep within the MIZ. And this is one of the other things, one of the few other publications we have from this long-term data set. We've mostly been just collecting it, and we haven't done a lot of analysis with it yet. And this is a nice bit of work by Vince Cooper and co-authors that is in that same special issue, the special issue for Vernon Squire. And so here's the link for it. You can find more on that here. And Vince went and looked at this data set, this long data set, and asked, when do I see waves deep within the ice? But I already gave you the spoiler on that. I already told you that we almost never see waves more than 100 kilometers in the ice. So he uses satellite ice products and asks, if I know about where the ice edge is from the satellites, and I look at these in situ data records, do I see waves deep within the ice? And mostly the answer is no, or not much. And then when we do see waves deep within the ice, more than 100 kilometers laterally in the ice, they're not what we expect. So let me walk you through it. First, what do we see in open water? In open water, we see these three panels here. The top panel is the wave heights, and it's how often we make a measurement, how often we see something. So it's just a histogram of the data. The wave heights tend to be, 1 to 2 to 3 meters, and occasionally we have a big storm and we see wave heights 3 to 4 meters. This is all in open water. In open water, we have all these measured spectra. I realize it's a tremendous amount of data on one plot, but this is frequency and this is energy. Spectra have a nice f to the -4 shape as we expect, and they have peaks that are determined by the fetch and the wind speed, etc. And then down here, you can do that same fetch scaling that I did earlier in the talk to demonstrate that fetch really matters in the Western Arctic. And you can see that most things lie along a fetch scaling. So the open water part makes sense, right? Now, if you look from 0 to 100 kilometers into the ice, you get the same plots here, and they're all in orange. And you see the wave heights are generally quite small. Occasionally, there's some larger wave heights. You see some spectra that are a bit more muted because of attenuation, that some of the spectral tails are really attenuated, heavily attenuated, and they should be, right? Because attenuation goes as, frequency to the sum power 3, 2 or 3, something like that. So that makes sense. And if
Jim, you are having 2 more minutes.
Roger, got it. 2 more minutes. Yeah. Okay. So I'll close out this slide and that'll be it. So the fetch scaling here shows that there is the energy lies below the fetch line, and that makes sense because these waves were generated somewhere else, propagated into the MIZ, and started to lose energy as they went into the MIZ. So they should fall below the fetch line. Now here's the fun part. If you go 100 kilometers into the ice, hopefully you can move the zoom thing out of the way and see that there are all these small waves in the ice, but they're very short period. Look at the spectra here. There's something like 0.3 in terms of peak, and they really look like a pure wind seed, and they actually match a fetch scaling, which is remarkable. And the argument here is that these waves deep within the ice are locally generated. They are not waves that propagate far into the ice. The waves in the Arctic are not long enough period or big enough to make it way deep into the ice. So locally generated waves happen, and they happen when there are leads. And that's my final point, is if you look at some satellite images over where one of the moorings is, so now this is in scales of kilometers, and you look at one mooring location, and this is a satellite image, you see that for much of the summer season, the Arctic is melting such that there are these stretches of open water that are 20 kilometers, 15 kilometers. That's as big as many lakes, and that's enough to have fetch limited wave generation. So we see all these small waves, these fetch limited waves in these patches of open water throughout the summer, because the marginal ice zone is such a diffuse and melted thing in the Western Arctic. And I think this is another thing that's sort of underappreciated in the literature, that we have these short wind waves sort of throughout the MIZ that are locally generated. Okay, I'm going to skip the coastal stuff and just remind you where the data is. So if you are interested in this data, you can contact me directly, or you can go to this link and you can download them. I have yet to post netcdf files, but I will. They're just MATLAB files right now. But I would love to see more people using this data set and exploring it. Thank you.
Thank you very much, Jim. Now it's time for question. There is a long chat. Please go ahead. Alex and Mike.
Keep sharing your screen, Jim, I think.
Okay,
yeah,
sure.
thanks a lot for your talk. It was great and great you made it as well.
Sorry about that. Entirely my fault.
So, Jim, do you reckon that energy, this turbulent dissipation, well, I guess the energy has to sort of go into turbulence in a way, right? That's the logical place. And the question is maybe what's the mechanism for turbulence, but do you think the turbulence that generally accounts, that's the right order of magnitude to account for the energy loss from your measurements?
Yes. Yeah, I think from our measurements, it often is. I will caveat that we have done most of those measurements in places where we can put our buoys, which tend to be smaller ice flows. So not big sheets, not enormous flows. And I think in those conditions, the ice is quite mobile. So it's really easy to move the ice around and stir the ocean below. I think if we were talking about big pieces of ice and that had lots of flexural gravity waves and lots of stress and strain in the ice, then that's not going to be true. You're going to lose a lot of the energy to things happening in the ice itself. But if the flow size distribution has mostly small flows, then I think, yeah, you mostly you stir the ice below. And I'll just one more thing about there's a nice paper by Maddie Smith where she uses some stereo observations to ask how elastic or inelastic are the collisions of small ice flows and how much would they lose energy every time they collide. That's just an ice-ice interaction that doesn't require the turbulence. And she concludes, I think, correct me, Maddie, but that is real, but an order of magnitude smaller than the turbulence below.
Yeah, because talk about these big flows, but my feeling is that once you get any kind of real waves going on, like that, it's going to break those flows up until they start to become small. It's creating and it's only when there's the length scale that ice is forming to that's small, and then you get down to this next. I think during that breaking process, there may be the wave front that's propagating in. If you get a sudden surge of energy, that may propagate slowly because it needs all this energy to break the ice up. And then you settle down to this equilibrium state with small bits of ice, and then the energy is being chewed up from this turbulence. Mm-hmm. That's what I'm thinking.
Yeah, I like that concept a lot, that there's sort of an adjustment phase. Let's say that the incoming waves are in steady state, and you've got hours of the same wave field coming in, that at first you'd take big pieces of ice and all the energy would go to breaking them up. And then you'd eventually adjust to this sort of quasi-equilibrium where now it is the turbulence. So at first the energy is going into ice breakup, and then later it's going into turbulence. And I think we would need different models to describe those different things, right? And we probably would have a change in the attenuation rate in the bulk sense and in the spectral sense between those two regimes.
Yeah, we need some measurements of that process somehow. But anyway, I'll let someone else ask a question. Thanks a lot, John.
Is there any other question? No. Thanks, Jim. You can now stop your screen sharing. Thank you very much. So we are now having 1 hour break. Then we are having the last session of this workshop. Professor Melan, if you want to say something, you can proceed.
No, I'll see you all in an hour. Thanks to all the speakers, though. Another great session. And so Simon's recorded all these talks.